So this has now led us to consider observables that are attached to space-time events. If I have an observable, I have to tell you when I will measure t and where I will measure x. And this has naturally led to the concept of a field. So let me explain that. One thing that we could try to measure in this room right now is the temperature. Now, let's imagine I'm going to measure this very precisely. So if I'm going to measure the temperature very precisely, well, I need to tell you when I'm going to measure it. You see, if I measure the temperature at midday when the sun is directly overhead and in summer, I'm going to get a much larger value than if I measure the temperature at midnight in the middle of winter. So when I make the measurement is definitely going to affect the answer that I get. But then apart from that, if I measure the temperature close to the window where there's a breeze which cools things down, I'm going to get a lower value for the temperature than if I measure it right next to my head. You see, I keep emitting heat. So my head is behaving like a radiator. So my head is heating up the air around it. So if I measure the temperature at a point right next to my head, it's going to be larger than if I measure the temperature close to the window. So to know exactly what temperature I'm going to measure, I have to tell you when I will measure and where I will measure. So this is an example of a field, the temperature field, and it's an example of a scalar field. It's just a single number, the value of the temperature, and it is defined everywhere and every when. And that's what we mean by a field. A field is something that can be measured everywhere and every when. Here it's the temperature. The temperature definitely takes a value at all points inside this room and at all instants in time. Now, fields don't just have to be scalar fields. We could, for example, consider the electric field. And for the electric field, we typically write E. We put an arrow on top to denote that it is a vector, E of t, comma, x. And this is an example of a vector field. Now, light itself is an electromagnetic wave. So if you measure the value of the temperature at all points inside this room, because there's a different amount of light at different points inside the room, the value of the electric field will be different at different points in the room. At night, when it's dark, the value of the electric field will be less than it is during the day, when it's very bright. And if there's a light inside the room, the value of the electric field will be larger, closer to the light bulb, than if you're further away from the light bulb. So again, the electric field is something that we could measure at all positions inside this room and at all instants in time. And that is an example of a vector field. So by looking at the constraints imposed by relativity, the fact that you can't move faster than light, we found that we have to say where we will make a measurement and when we will make a measurement. So we've been led naturally to the constraint. We are told that observables must be fields. Okay, so this is what we learn from special relativity. Observables must be fields. Good. Okay, let me just clean a little bit more space. Maybe we don't have to clean everything, but let's clean a little bit of space here. Okay. Now that I know what constraints special relativity puts on what can be on our observables, let's ask ourselves, what constraints does quantum mechanics put on our observables? Okay. And the basic constraint that comes from quantum mechanics is the uncertainty principle. Okay, so quantum mechanics. And the basic constraint here is the uncertainty principle. And what do we mean by the uncertainty principle? Well, Heisenberg's uncertainty principle tells us that delta x, delta p is greater than or equal to h bar over 2. So let's start off by discussing this equation and trying to get some idea as to what it means. This equation could mean two very different things. The first thing that this equation might mean, it might be a statement about how well we can measure. It might be saying, well, we're not very good at making measurements, so we always make errors, and this is the size of those errors. So that's one possibility. This statement, the uncertainty principle, might be a statement about our ability to perform experiments. But it might also be a statement about nature. And what I mean by that is the uncertainty principle might be telling us that the idea that there is a particle that is located somewhere and it has a specific momentum is just wrong. That's not what reality is like. The idea that there's a particle sitting somewhere with some momentum doesn't exist except in our imagination. In that situation, the uncertainty principle is a statement about reality. Well, some discussions of the uncertainty principle, like, for example, Heisenberg's microscope, would lead you to suspect that the uncertainty principle is a statement about our ability to make measurements. That's not true. In fact, the uncertainty principle is a statement about reality. So let me try to explain why that's the case, okay? So the key idea here is that observables are Hermitian operators. Okay, maybe the important point is that observables are operators. Okay, so I'm talking about non-relativistic quantum mechanics here. So in particular, I'm not considering energy and matter to be equivalent. So there's no pair production. So in that situation, the momentum P is an observable and the position X is an observable. So these are my observables, okay? If I have got the state of a particle and it has some definite momentum, then what that means is if I take the momentum operator and I act on the state of my particle, I will get some eigenvalue P times by the state of my system. In this case, I would say, well, my system has momentum P. Equivalently, if I have some state of my system, let's call this phi, and I measure the position and I find it's got some definite value, that's equivalent to saying, if I take the position operator and I act on the state of my system, phi, I will get x, the position of my particle, times by the state of my system, phi. So this is what it means to say I've got a definite momentum. I'm an eigenstate of the momentum operator, or I've got a definite position. I'm an eigenstate of the position operator. Now, we now want to make a statement. If two operators do not commute, you can't find simultaneous eigenvectors for them. And I want to unpack the statement a little bit and figure out what it means. We'll do that in a moment.